Okay, the recorder cut off about a little less than halfway through that last clip, but let's go ahead and pick it up. The last thing I wrote was that y2 was e to the negative 2t, and I was just plain careless about that. And I was also careless about a couple of other things, and I don't know whether I'd fixed those by the end of the clip. I'd written e to the 1 lambda instead of e to the 1 t. And then I'd written e to the lambda t. Well, that would have been right, except lambda we've already seen as 1, so that should have just been e to the t. So that now this reads correctly, so let's see where we go with the rest of the solution. First of all, we can see that y1 equals e to the t and y2 equals negative 2e to the t are indeed solutions to our original equation. Now I'm just going to point this out. I'm not going to write it out. I recommend that if you don't see everything in your head, you should write this out. But if I plug in e to the t for y1, I get 5e to the t. 5y1 is 5e to the t. If I plug in negative 2e to the t for y2, I get 2 times that, negative 4e to the t. So I'm going to have 5e to the t minus 4e to the t, which is equal to 1e to the t. And that should equal y1 prime. Well, y1 is e to the t. Its derivative is e to the t. So this checks out in the first equation. And you can do the same thing with these functions in the second equation. You are going to end up with y2 prime, which is negative 2e to the t. And if you add 4 times this and 6 times this, you do get negative 2e to the t. The next step is to solve the matrix equation. Okay, the matrix equation here for lambda equals 7. And that's very easily done. We just plug in 7. 5 minus 7 is negative 2. 2 becomes 2. 4 stays 4. And 3 minus 7 becomes negative 4. That leads us to the two equations. Negative 2x1 plus 2x2 equals 0. And 4x1 minus 4x2 equals 0. These equations are just, they're degenerate. One is a multiple of the other. The second equation is just negative 2 times the first equation, as you can easily see. So both equations have the same solution, and that solution is x1 equals x2. And it's going to be solved for any time x1 equals x2, because if x1 equals x2, clearly negative 2x1 and 2x2 are going to be equal and opposite and add up to 0. So we make the simplest choice. x1 equals x2 equals 1. And that gives us what? That gives us a solution to our eigenvalue equation. And let's see, where in the world did it go? Let me pause for a minute. Okay, I had it right there. I just wasn't seeing it. Our y1, y2 column vectors, e to the lambda t x1, x2. Plugging in lambda equals 7, we get e to the 7t. Plugging in x1, x2, both equal to 1, we get 1, 1. If we multiply this out, we see that y1 is e to the 7t, y2 is also e to the 7t. And we can plug y1 and y2, these functions, into our original equations and easily see that if we do 5 times this and 2 times this, we get 7 times e to the 7t, and the derivative of y1 is 7 times e to the 7t. Similarly, the derivative of y2 would be 7e to the 7t, and that's what we'd get if we do 4 of these and 3 of these. Once more, write that out if you don't immediately see it. Now we want to write the general solution to our system of equations. And at this point I need to introduce some notation. And the notation here, and I've never found a good way to get around it, the notation here gets a little bit confusing. So if we go back here, you might have noticed that I've inserted a vector equal to y1, y2. And that vector I've called big Y of t, and I put an arrow over it to indicate that it's a column vector. That's to distinguish this y from these y's. This y and this y refer to functions of t, just plain old functions of a single variable t, whereas this big Y with the arrow over it refers to a vector function, a column vector, a function with, in this case, entries in each of the first two rows. I do that because what I want to do is I want to write my general solution as some multiple of my y1 function plus some multiple of my y2 function, where my y1 and y2 functions are these solutions to the matrix equation, to the eigenvalue equation. And I haven't used that term yet, but the lambda is called an eigenvalue, and these are called eigenvectors. You don't need to remember that terminology right now. You'll become plenty used to it before long. Okay. Now this is confusing because our form of our solution is y1, y2. Now we got a y1 and a y2 vector up here, or y1 and a y2 function up here to make up this column vector. But now we're going to call this column vector vector y1. We also had a y1 and a y2 for the lambda equals 7. And those are different than this y1 and y2. But we can see how they were put together to construct this solution, and this solution is the one we're going to call vector y2, the e to the 7t times the 1, 1. So that when we do our general solution is a y of t, and it's a vector y of t consisting of two scalar functions. And this vector function is going to be c1 times the vector function y1 plus c2 times the vector function y2. And when if I multiply these out, I'm going to get c1 e to the t here, I'm going to get c2 e to the 7t here. And I'm going to get negative 2 c1 e to the t plus c2 e to the 7t here. And that's going to be another y1, y2 column vector. So we can see that the y1, y2 column vector is just a general variable. In this case, it has this value. In the case of lambda equals 7, it has this value. In the general case, it has this value. The y1 and y2 vector functions, on the other hand, have very specific definitions. And it's the combination of these vector y1 and y2 functions that gives us this vector y1, y2 column vector. y1 and y2 in this case being simple functions of a single variable, scalar functions of a single variable.